Okay, so today we're going to speak about one of the landmark papers in computer vision, which is called You Only Look Once, or YOLO. And this was really a big progress in object segmentation. So Dan is going to present it for us. He works as a data scientist for Nplan. And yeah, go for it.
Cool, thank you. So yeah, as Carlos says, we're going to look at this paper YOLO today. I guess I wanted to start off by actually just providing a little bit of context around the paper and sort of linking it back to a couple of object detection papers we've done recently. Carlos and Joao, both 3 and 2 weeks ago, were talking about object detection papers, and they were this one and also faster RTNN, which I talked about 2 weeks ago. So they're a method of object detection that actually uses a pipeline of networks, essentially, or a combination of networks to both divide up the space of your image and also then following that in a separate network to classify those subsections of the image. Now, the step change with YOLO is to combine all that into a single network. And maybe it's just relevant to actually look at this this review paper that I found. It's got a little flowchart here that sort of shows how object detection networks sort of split up into these 2 subsections, which are region proposal based, like faster RTNN that we looked at with Joao. And so we're proposing regions with a network, and then we're using the regions with a standard classification CNN to get the classifications out. Whereas this second stream, if you like, of types of network, they try and do everything in one hit. And you had a few of these papers before that attempted to do something like this, but the first one to really gain traction and to get quite a lot of success with it was YOLO in 2016. So that's where YOLO fits in the rest of the literature. Right? We've got all this exciting stuff on the other side, but for now we're just going to think about what things were like in 2016 and how YOLO changed things in terms of how object detection could be done. So yeah, maybe we'll talk quickly about what they were trying to do. So part of the reason that you might want to simplify your object detection network is because you want to do it a bit faster. And I think one of the uses of networks like this that gets called out quite a lot is with respect to self-driving cars and looking at video from self-driving cars and very quickly getting out detected and classified objects from this video. And so one of the things that is sort of championed in this paper is how fast doing things this way is. And they talk about even with the first iteration of their architecture being able to get good classifications out at 45 frames per second, which, you know, that was a massive step forward in how fast networks like this could provide object detection within an image. So that's why they were trying to speed things up, and perhaps now it's worth sort of delving a little bit into how they might try and speed things up. So the big novel change that they made was sort of reframing the problem as a regression problem. And now it's not your standard regression problem, it's quite a complicated regression problem, but we are looking for a set of continuous numbers. And so we're framing this whole thing as a regression problem instead of standard classification. And to do that, they've basically, they've chopped the problem up in quite an interesting way. So they take an image and chop it into an S by S grid, and each grid cell, can everyone hear me okay?
Yeah, we lost you there for a second.
Okay. So what I was saying was, for each grid cell, if the center of an object falls within the grid cell, then that the index becomes responsible for detecting the object. And then from each grid cell, we're predicting B bounding boxes. So I don't know if there's a diagram here, but we draw bounding boxes with a certain spread around that central grid cell, and we do so with a few parameters. Basically, we're skewing it by X and Y, so we're moving it away from our grid cell with coordinates X and Y, and we are sizing it with width and height parameters as well. So yeah, we're using those, and then we are also trying to get of this bounding box, which is a confidence, right? A confidence of an object being in that box. And so we have say labeled data with boxes, right? And they're defining this confidence as it takes into account the intersection over union of the ground truth box and this predicted box. So we've got 5 parameters about our boxes. We've got S by S grid cells, each with B boxes. And so that's the sort of box drawing portion of the network, or portion of the problem formulation. Alongside that, we've also got a class probability prediction portion of the network, or of the problem formulation. So we remember that each of the grid cells may contain the center of an object, and so each of those cells should also have an accompanying class probability, right? And that doesn't, they make an interesting point here. We only predict one set of class probabilities per grid cell, regardless of the number of boxes. So we're only going to be able to detect one type of object in each grid cell. And one of your boxes is going to become the detector box, if you like, of that grid cell. So yeah, we end up with 2 streams, if you like, 2 numbers that characterize the cell, one number that characterizes class probabilities within the cell, and one number that characterizes the probability of the box being the correct box for that cell. So they are, so I'll zoom in a bit so we can see this. This class probability and the box confidence. So when we're testing, when we're trying to get predictions out of the network, we predict these 2 and multiply them together. Okay, so that's how they've reframed the problem. And that gives us a predicted output of a tensor of this shape, right? So the S by S for each of the grid cells, the B times 5. So we have B boxes per grid cell, and we have 5 predictions per box. And then we're also getting the class predictions for each of the cells as well. And then, yeah, we're seeking to find a network that allows us to regress on this target, basically. Find the tensor that most closely matches this target. Okay, and so they provide an example here of how you might do it on this dataset Pascal VOC, and they use 7x7 grid over the image, and they predict 2 bounding boxes per grid cell, and there's 20 label classes, right? So you can see in this diagram that we've gone down 2 streams here, right? We've got the bounding boxes, and we've got the class probabilities down here. So we actually, there's an important part to mention. Say again, Carlos.
Yeah, I just wanted to point out something that I found interesting in this bit is that if you go back up to the image of the dog, so because the central position is calculated with respect to the center of the cell, the width and height of the bounding box is actually computed with respect to the size of the image. So you can see it here that even for a given bound for a given box, so for a given box in the grid, the bounding box can be outside of the grid as well, which I found super interesting. So when I first saw this image, it was a bit confusing because you can see that the bounding boxes are not really bound to the grid.
I see what you're saying. Yeah, they're not integer values that are computed against the grid cell. No, I think the grid cell just how can I say it? It tells you what granularity at which you can detect objects, right? Because you can only detect one object per grid cell.
Yeah, so the center of the box is calculated with respect to the bounds of the box. So the center has to be in the bounding box, in the grid cell, but the width and height are predicted relative to the whole image. So yeah, so which is a very interesting approach, because you're saying, well, you're actually regressing on the probability of the center of the image being in your grid and the size of the image being in the whole, and the size of the object being in the whole image, which is an interesting way of framing the problem, I think.
To me, that makes sense though, because the way that they've framed their problem, you could have an object that you could have an object that is much bigger than a single grid cell, right? That could its center falls within a grid cell, but it's much bigger than that grid cell. So it makes sense to center your box inside the grid cell and stretch it outside. What about that is interesting to you? Or
Just what I find interesting about this approach is that it saves you the trouble of having to join all the bounding boxes that you find. Because so if you see the lower branch, it's the class probability map, right? So if you wanted to do the object segmentation just from this class probability map, you would probably need a fairly complex algorithm that allows you to join those class probabilities, right? And then you would not be able to detect overlapping objects. But with the algorithm that these guys are proposing, you can detect the overlapping objects because you can see that the center of the dog is in a different grid point than the center of the bike.
Yep.
So it's quite interesting. Bahan asked, are class probabilities max values from softmax? Does that mean grid sizes don't matter very much? So they're not values of softmax. They are the output of the last convolutional layer, as far as I remember.
Yeah, I think.
And the grid size matters because of what I said before, because you have to find the grid point that has the center of the object in it. So if your grid is too coarse, it might be that both objects fall within the same grid point. So both centers fall within the same grid point. And then you're not able to predict both. You're not able to find both.
Well,
so the grid size
you wouldn't even train on both, right?
Yeah, indeed. It's what you said before. You can only predict one object per grid point. So you wouldn't find. So let's say if you divided the coarseness of this grid, if you multiplied it by 2. So if you well, this is odd, right? Well, let's say you make the grid coarser here.
Yeah. If that was one grid cell.
Yeah.
Then the center of the dog and the center of the bike are in a single grid cell, and then you
can probably detect both objects, but you would not be able to segment them properly. Should we carry on?
Yes, let's do it.
Sorry about the interruption.
No, I think that's quite a relevant point, actually. Yes, I don't know where it mentions about how X and Y are scaled. Sorry, I'm not sure if you can remember. Yeah, here we go. Okay, so yeah, this is basically what Carlos has said here, right? So then they've normalized the bounding box width and height with the image width and height and the X and Y offset within the grid cell. So yeah, I guess that summarizes what we were saying just now. Yeah, I think it's worth at this point talking about how they've actually structured the network. Maybe that can answer Vahan's questions about softmax in a little bit more depth. So yeah, as is common with these papers, and we've been discussing this in NPlan a little bit, it's basically just a bunch of convolutional layers stacked together. And they've got the majority of it from this LeNet model for image classification, right? And then they've appended a couple more convolutional layers on the end and the start, so that their output tensor is fitted correctly, basically. And they do a pre-training step. So they pre-train the majority of the convolutional layers on ImageNet to try and get things roughly where they need to be, I suppose. And then they append these convolutional layers to the front and the end. 4 convolutional layers and 2 fully connected layers. And they do that to make sure that they have the output of the right size to solve the problem that they formulated. And then they talk here about this normalization step, as we've said, and some specifics of how they structure what activations they use, and then I think the next interesting part really is, and quite a relevant part, is to talk about the loss function, and they sort of lead up to it in this portion here, of how they're constructing the loss function that they're trying to optimize, right? So maybe if we just jump into what the loss function is, and we can then see why that they've done each of these terms by going back up and looking at the little passage they've written. So this is the loss function they've designed, and I guess you can break it down into 3 parts. Maybe is the right way to think about it. So these top 2 terms are the terms that help you get the right box, right? So, or the right set of boxes. So summing over all the cells and over all the boxes in each cell, and we're checking if we have an object that's centered in the cell. So this is what this is saying, and if actually, sorry, I'm going to have to step back one second to explain these indicator terms, actually. So our most confident box from the cell, so we've got B boxes, and each of them will have an associated box confidence that we defined earlier, this box confidence here. And so we have ended up with a set of boxes with a set of confidences, and the one with the highest confidence becomes essentially the responsible box. That's what they call it for that cell. And so we index into that box by using this indicator here. So we're looking only at cells that contain centers of objects, and only at boxes that are the responsible box for that cell. And we are seeking to optimize the square difference of the center position, as we were talking about earlier, between 0 and 1. So we'll have, if for each box that has an object within it, we'll have a target. For each cell that has an object within it, we'll have a target box. And so we're trying to find a matching center here. And for each box, each cell with a target box will have a target width and height. So that's what we're trying to match here. Now at this stage, we're trying to, let me get this right. I think this is optimizing the box confidence.
Yep.
Right? So yep. I can't quite recall, Carlos. Can you remember exactly how this is being done?
Yeah. So it's actually, it's just as you say, it's trying to tune the confidence, because so I think that one thing that may be confusing is that these are not actually probabilities. So it's called confidence. If you see before, they use a linear unit for the output layer, which means that they don't need to add to 1. It's just saying it's a high number if the algorithm thinks that object C is going to be there, and low and lower if it thinks that it is less likely for the object to be there.
Okay.
So yeah, what this second term is trying to do, and maybe it's easier to think about it in that they use only two two bounding boxes per grid cell. So it is just trying to say, well, take the one you gave the most confidence for and see if it is actually the correct object. So if it is not, it's going to penalize that high confidence that the network gave, and if it is going to reward that confidence. And then you have the no object, which I think it's the other one, right? So
yeah, so it's all the boxes that don't have the weight. That's right.
And yeah, so they try to formulate the problem in a very generic manner, but if we think about them as only two boxes, it's you're computing a loss for each of the boxes.
Yeah.
So
okay.
if you get otherwise you can generalize it by saying take one box and put it in the top term and sum over the confidences of all the other boxes and penalize all those if they are wrong, or reward them if they are right.
I suppose the thing that wasn't clear to me straight away was what is a target confidence for a box?
I mean, I'm not sure if they have that in the data set, or if it's just saying that is the right object or not.
Yeah.
But yeah, that's what they're doing.
Fair enough. There's a question from Alexander, I think. So I'll answer that. He's asked, why are there square roots on W and H? And they do address that in one of these paragraphs up here. So they said some square errors also equally weight errors in large and small boxes. And yeah, they're essentially saying that if we move a big box a little bit and we move a small box a little bit, then moving the big box matters less than the small box. So they've said that doing things this way ought to remedy that. I think that makes sense to me. Because yeah, okay, cool. Alexander says it makes sense. Cool. Yeah, so the final term, after we've got our box sizes and confidences, is to optimize for class probabilities as well. And it's worth noting that we are only optimizing these class probabilities in cells that do contain an object. So that's what this indicates referring to. When it's only got a single index, we're indexing over the grid cells that contain objects in the true image. So this is the kind of novel, well, not novel exactly, but like the interesting loss function that they're using to try and solve their problem that they've structured. And they go into some specifics of training down here as well. But yeah, probably not relevant to go into that stuff at the moment. And then they talk briefly about some limitations. So one of the limitations that we talked about is each grid cell can only predict a single class. And so that limits how close objects can be to run at the same speed that they're running things at with like quite a coarse grid. The objects actually have to be kind of far apart in the image. They talk about aspect ratios of the boxes, which is something that gets addressed in some of the later iterations of this paper. but maybe we'll save that for another day. And again, they note that the loss function is not agnostic to, well, it is agnostic to box size, which probably isn't too good, right? So yeah, they're highlighting some problems with this loss function, basically. And then they go on to compare to the way things are at the moment back in 2016. So they refer to some of these networks that I mentioned in this review paper back here and over here. And they talk about increase in speed and some slight decrease in accuracy. That's essentially the conclusion, really, is that they've got a negligible or very small decrease in accuracy, and they back this up with some experiments, as I say down here. That's link. So they link back to RCNN and think about where the error comes from in RCNN and where it comes from in Yolo. And so they are basically saying that they're getting comparable error with RCNN, but at a much higher speed. And they go further as well and combine some of the parts of RCNN with Yolo to increase the accuracy that they can see from either of the networks on their own. They do talk as well about how Yolo can generalize slightly better than RCNN, and they do that by looking at artwork instead of photographs, and see some success basically in seeing and detecting people in artwork rather than in images, photographic images. And then they go on to describe this basically toy that they've made to do object detection with webcams. And so it's an interesting paper, I think, and one that was a bit of a step change in how object detection was done, and presents quite a lot of ideas that do get built on a lot in subsequent papers by the same set of authors that, yeah, address some of the concerns they have about the network and the way that this loss function is built. So I hope I covered the majority of what people are interested in. There's another question here. When we train the model on our own data set, is B the number of bounding boxes? Is it a tunable hyperparameter, or is it a fixed number, which is 2 in the paper? I don't see why you couldn't tune that as a hyperparameter. I think a higher number of bounding boxes would take longer to train. But I see no reason that you couldn't increase that number at all. I don't know if you want to jump in, Carlos.
Yeah, I don't remember them discussing why they chose 2, but surely it depends on the resolution of your image and how many objects you're expecting. So how much you're expecting objects to cluster together, I guess.
I suppose so. I think more bounding boxes wouldn't give you more in the way of, it wouldn't give you more in the way of images, objects close together, though, would it?
Yeah, well, because I don't know, I think that because of how they structure the training, which is that they only define the loss on the bounding box that has the biggest confidence, right?
Mm-hmm.
So I don't know, intuitively, and I would like to hear someone else's opinion on this, because I'm a bit going by by intuition here. If you have more bounding boxes, then it is harder for the algorithm to optimize, because because you basically have too many negative confidence terms in that second term of the loss, right? So I think that
this is their reasoning for using these weighting parameters, right? And they really down weight the negative examples.
Yeah. So yeah, I guess you just have more hyperparameters to play around with, and maybe they just found that they didn't need more bounding boxes.
Yeah, I think my gut was that does it allow the network to explore different box shapes? If you've got two, then it's got two shots at getting a reasonable start at a bounding box that can then quickly grow to the right size.
Yeah, well, I guess as long as you are working just with square boxes, so well, which is a bit of a repetition, but as long as you're only working with width and height, there are only two aspect ratios that you can try, right? It is either larger width than height, or larger height than width. I don't know, does that show in the? I don't think it shows very well, but I don't know. I'm going to go and say that they wanted to make it a hyperparameter, and then they found that 2 was just fine.
I think you're probably right. And one of the changes that that does get made in one of the following papers, I'm not sure which it is, but they increase the number of bounding boxes, but set them all off at, or they have what they call anchor bounding boxes. And these are like a set of common aspect ratios that you might expect to see in your image. So if your situation is you want a model to detect people and cars, there are common aspect ratios of cars and people in an image. And so you'd set your bounding boxes to start with those two anchors. And then one of them will get a higher confidence, and it will end up becoming your responsible bounding box. And I think they kind of said as well that you end up getting boxes of certain aspect ratios if you choose to train on only images with those aspect ratios in, which is worth noting, I suppose.
Yes, I think that one of the other interesting things about this paper is that if you go to section 4.3, is that they actually acknowledge that fast RCNN is a good detection algorithm. You know, they don't just say, oh, look at all these limitations and now you have to use Yolo, but they actually explore that combining Yolo and fast RCNN can actually give you a boost in performance. And they reason it in a very interesting way, which is that because Yolo is and that shows up in the pie chart above, is that because Yolo makes fewer background mistakes, you can use but fast RCNN has better mean average precision. So you see the correct bit of fast RCNN is larger than Yolo, but the background mistakes in Yolo is smaller than fast RCNN. They say, well, combine them both in a way that in a way to eliminate background noise. So they sort of boost fast RCNN if Yolo predicts a similar box, and they improve. Like they have a 3% increase in
I mean, it's
in mean average precision, which is quite interesting.
Yeah, definitely. Okay. So Bob asked for the link to review the review paper and got it, I think. Yeah. I wonder if anyone else has any further questions about this paper. I'll do my best to answer them, or at least foster some discussion about it. I think it's a really interesting way of thinking about the problem. That if you requires a bit of thinking outside the box, if you'll pardon the pun. And yeah, it clearly works, right? It gets fast results and does it with, I mean, reasonable accuracy. And like I say, they have a set of papers that are similarly titled, that are sort of incremental changes on this ground idea that go some way to improving the problems with YOLO. And that's like reframing the bounding box problem and slight changes to the loss function that, you know, help to deal with some of these problems. So it's definitely worth looking into if object detection is something you're interested in.
Yeah, for sure. So if there are no more questions, I'll just stop the recording.